Okay, in this video we're going to learn another rule, another derivative rule, which we call the chain rule. So we already kind of know part of the chain rule. So let's look at this example together. I want to get the derivative of this function h of x. And we have a rule which allows us to do this. Remember, this is what we call the power of a function rule, right? There's a power of a function. So the rule for the power of a function rule was you take the derivative of the power part. So it's the power of 3. So the 3 will become the coefficient. You leave the function as it is. So the inside function, the 2x plus 1. And then the power goes down by 2. And then you have to multiply by the derivative of the inside part. So the inside function. So the derivative of 2x plus 1 is just 2. And then you can simplify. We have a 3 and a 2 as constants. So those can multiply to give us 6. 2x plus 1 squared. So this is what we call the power of a function rule. But the power of a function rule is not, it's not really a rule on itself. The power of a function rule is really just a special case of what we call the chain rule. So let's look at this here, this function h at x. So we call it a power of a function, but we could also think of this as a composite function. So this is a composite function. If you remember what a composite function is, a composite function just means one function inside of another function. And in this case, the sort of outside function, or the function which is not the inside function, is a power function, which is why it's a power of a function rule. But a composite function just means one function inside of each other. So for example, we could write h at x as f of g of x, where one function is inside of another. So where g at x, the inside function, is the linear part, the 2x plus 1. And f at x, the outside part, is, you can think of it as, actually what I'll do here, I'm going to use a different variable. So let's say u. F of u is u cubed. Just, you can use x, but when we explain this sort of the first time, just to kind of make things clear, we often use a different variable just so you can think of it as a little bit differently. Okay, so let's say f of u is equal to y. So like y is the variable which depends on u, and then u would be a variable which depends on x. Okay, so we've got these two functions, and then we put them together to get h of x. So what I'm going to do here is I want to take the derivative of each one. So g of x is 2x plus 1. So what's the derivative of g of x? So g prime of x is 2. And what's the derivative of f, or f of u? So f prime of u is 3u squared. So if I were to multiply these two derivatives, f prime of u, so notice f prime of u times g prime of u is equal to 3u squared times 2, which equals 6u squared. But remember, u is equal to g of x, which is 2x plus 1. So just substituting, this should have been an x. Just getting everything into x, you would have 2x plus 1 squared. So this is the derivative, right? If you just multiply the derivative of f and g, and that's the chain rule. So the chain rule just says if you have a composite function, so one function inside another function, you can take the derivative of the inside function, which we did here, and the derivative of the outside function, which we did here. And if you multiply those two things together, you will get the derivative. And the reason it's the derivative, remember when we did it over here, it's the same thing we got over there. So that's the chain rule. I'm not going to prove it formally or in a general case. We just kind of proved it with this example or saw that it worked for this example. But I'm just going to write it down for you here. Okay, so here is the chain rule kind of just written down. So if you have two functions, f and g, that are both differentiable, and then you take the composite, so I'll call that big F, which is g inside of f, then f, big F prime, so the derivative of this composite function, is just the derivative of f evaluated at g times the derivative of g. So it's just the derivative of the outside function times the derivative of the inside function. The one thing you have to remember is you're evaluating the outside function at the inside function. Or in Leibniz notation, this is another way to write it. Remember I said, you have your function f of u. You can think about f of u, your outside function being evaluated at u, and then your inside function is equal to u, so u equals g at x. Then in Leibniz notation, this becomes the derivative dy by dx, so that's the derivative of the whole thing, is equal to the derivative of the outside function times the derivative of the inside function. So this would be dy by du, and this derivative would be du by dx. So you just multiply the two. This is might be a little bit confusing if you don't see an example. So I'll do an example where we kind of use these variables so you can see it separated like this. Okay, so here's our example. We want to differentiate y equals x cubed minus 1 all to the power of 100. So here's a composite function, right? The inside function is this cubic thing, and the outside function is the power of 100. So the outside function is to the power of 100. So what I'm going to do is I'm just going to write it kind of different, just so you can see different variables to kind of make the composition, the idea of it being a composite more explicit. So y is equal to u to the power of 100. Okay, so I'm replacing this inside function with just a single variable u. And then u is equal to u cubed minus 1. So the u is just, not u cubed, x cubed minus 1. So u is become this inside function. So if I were to put u x cubed minus 1 in for u here, I would have this. So what I'm going to do is take the derivative of each of these two. So dy by du is equal to, so that's just the straight power rule, so 100 u to the power of 99, and then du by dx is equal to 3x squared. So what the chain rule tells us is that the derivative of this is just the product of these two derivatives. So dy, therefore, dy by du is equal to dy by dx is equal to dy by du times du by dx. And dy by du is 100 u to the power of 99 times 3x squared. Du by dx was 3x squared. And now I'll just simplify by multiplying the constants. So that's 300 u to the power of 99 times x squared. Now, I don't have the same variable, right? I have x and u. So what I'm going to do is get everything in terms of x. So take u, which is equal to x cubed minus 1, and sort of substitute it in there. So this is equal to 300 times x cubed minus 1 to the power of 99 times x squared. And that's the derivative. Now you might say, well, like, why would I separate it like this? I just separated it like this to try to make the chain rule idea clear about how you're just taking the derivative of the outside times the derivative of the inside. Now you might look at this and say, well, that's just the power of a function rule, and it is. The power of the function rule is, it's not the same as the chain rule, but it is a special case of the chain rule. So when you do the power of a function rule, it'll look the exact same as the chain rule, because the chain rule, when you do the power of a function rule, you're doing the chain rule. It's just the outside function happens to be a power of a function.